Imagine measuring something moving at 186,000 miles per second, using only gears, mirror, and pure ingenuity. In 1849, that's exactly what French physicist Hippolyte Fizeau did. Today, I'll tell you how, and how I recently recreated his experiment on the Texas coast with modern tools, a laser, a telescope, and a fast spinning wheel. In the mid 1800s, scientists suspected light was fast, but no one knew how fast. Fizeau devised an elegant method: shine light through a rotating wheel and reflect it off a distant mirror. By seeing whether it returned through the same gap or was blocked by the next tooth, he could measure how long the round trip took. That timing revealed light's speed. Inspired by his work, I headed to McFadden Beach with a 5-watt green laser, a 4-inch wheel on a Dremel tool, and a retroreflective target 4.04 miles away. My wheel had 100 slots and 100 teeth. I focused my telescope's camera through the slots, watching for the reflected laser pulse. A visual tachometer tracked the RPM. Well, in 1849, Fizeau used an oil lantern and clockwork to spin a large 20-inch wheel. His mirror was 5 miles away. At 756 RPM, the returning light beam got blocked by a tooth. Proof that he had the timing just right. From this, he calculated the speed of light at 313,000 kilometers per second, only 4.4% off from today's value. On my shoreline setup, the round trip was about 47 microseconds. At 6,400 RPM, my returning beam flickered out, blocked by a tooth. Now, why did I need such a high RPM when Fizeau got away with just 756? Well, his wheel was 20 inches. Mine was 4. He could fit more slots, and his beam traveled 20% farther. Even so, using my mosquito-tormented data, I got a result close to the modern value. Not bad for a beach, a Dremel, and a laser pointer. So who came closer, me or Fizeau? Let's do the math. In order to complete this experiment, I needed to know 3 things: the distance to my retroreflector, the number of slots plus the number of cogs in my wheel, and how fast I was spinning the Dremel. The distance is a constant, 6,501 meters. So is n, 200. I had to figure out the frequency, and I came up with 6,400. Turning that into a period, that comes out to be 9.375 milliseconds. Dividing that by the number of slots, 46.875 microseconds. Well, speed is nothing but distance over time. We have to double the distance because it's a return trip, and we already know our time. That comes out to 277 meters per microsecond. Put that into seconds, it's 277,376,000 meters per second. Let's convert that to kilometers. 277,376 kilometers per second. If you recall, Fizeau, he came up with 313,000 kilometers per second. Today's value is 299,792. So who came closer? Fizeau beat me with 95% to my 92%. But let's be honest, he worked on this experiment for 2 years. I thought about it for about 2 weeks and spent 3 hours at the beach conducting it in one run, and mosquitoes were incredible. Fizeau's experiment confirmed that light has a finite, measurable speed, laying the foundation for giants like Maxwell with his work on electromagnetic waves, Lorentz in his framework theory explaining how measurements of space and time change at high speeds, and of course, Albert Einstein's earth-shattering theories of relativity, where he explicitly cited Fizeau's work. By channeling Fizeau, I didn't just revisit history. I remeasured one of the universe's fundamental constants, from a physicist using candlelight in 1849 to my laser on the Texas coast. Measuring the speed of light shows how clever experiments illuminate the mysteries of the universe. Pun intended. Thank you.